Hey everyone, welcome back. Welcome to Lesson 6 in Unit 9. Today's topic is Le Chatelier's principle. So in the last video, we talked about collision theory and rates of reactions. So how do we get a reaction to actually happen? And then once that reaction is happening, how do we get it to speed up? Now today, we're going to talk about something called Le Chatelier's principle, equilibrium, and reaction shifts. So you'll see how all three of these things are related. So before we can move on, let's first cover the difference between irreversible and reversible reactions. So if something is irreversible, that means the reactants form the products. That's it, you're done, no going backwards. So you have A plus B giving you C. That's it, can't go back. But if we have reversible reactions, the reaction can go forward and the reaction can go backwards. So for example, we can have E plus F make us M and N, and we can go backwards and say M and N can make E and F. So if you see this double-headed arrow, that means it can go forward, it can go backwards. And so these are the types of reactions we're going to focus on today. So equilibrium, next big thing we need to talk about, is when the rate of the forward reaction is the same as the rate of the reverse reaction. So the speed at which you go forward is the same speed as which you go backwards. And so this only really happens in a closed system, meaning you can't just get rid of stuff because you feel like it. You can't just add stuff because you feel like it. Another thing to mention is that once you've reached equilibrium, so you have the same rate. So forward rate equals the reverse rate is concentration. And so this is the same as the amount of something is constant. And so constant just means it does not change. And so once you've hit equilibrium, what you make is the same as what you lose. So for example, we have A plus B making C and D. So if you're going forward, you're making C and D. If you're going backwards, you're making A and B. But at equilibrium, the speed at which you make C and D equals the speed at which you make A and B. And so the concentrations, the amount of stuff you have, doesn't change. So if you used A and B to make this, well, you just use this to make that. And so it's like one step forward, one step backwards. Once you've reached equilibrium, concentrations are constant. And so constant doesn't necessarily mean equal. And so this example right here on the bottom is kind of a good way to think about it. You know, you have this closed system, you can't introduce or remove fish, but we're at kind of this equilibrium, meaning, you know, the concentrations, you still have 10, but you have 1 and you have 9. That's not changing. So constant concentrations equal rates. And so we're going to keep revisiting this over and over and over again. Constant concentrations, same rate. So again, equilibrium, these two graphs show this pretty well. You have your rate or your speed. So in this case, you know, the speed of the reverse speeds up and the speed of the forward reaction slows down. And when you have the forward and the reverse equaling at the same rate or the same speed, this right there is when you start to hit equilibrium. Now again, you have your constant concentrations or amount. And so for here, you're at equilibrium, you have more products and less reactants. Again, that doesn't necessarily, that works. Constant doesn't necessarily mean equal. We know this is equilibrium because the concentrations are not changing. And so it's kind of like thinking of walking on a treadmill or trying to go up a down escalator. The speed at which the guy is walking up is the same as the speed of the escalator going down, so he is not going anywhere. Okay, so there are a few types of equilibrium that we should cover just pretty quickly. By the time you kind of see how this all kind of is the same thing. So phase or physical equilibrium talks about the rate at which one phase change happens. The opposing phase change occurs at the same speed. So for example, the rate of melting equals the rate of freezing. And evaporation and condensation would be the other one. So this picture right here shows the rate of vaporization. So the amount of things that are turning from liquid to gas is the same as the speed of the gas particles turning into liquid. So when those two speeds are the same, that is that phase equilibrium. Next, we have solution equilibrium. And this is talking about the speed at which something dissolves is the same speed at which something recrystallizes. So dissolving and undissolving. So this picture kind of shows that there. Again, it's all about the rates being equal. And then we have chemical equilibrium, and this is the one we're going to focus on the most. And you have the rate of the forward reaction equals the rate is equal to the rate of the reverse reaction. So in this Haber process example here, you use N2 and H2 to make NH3, but you're also using NH3 to make N2 and H2. And so the rate of the forward, the speed at which NH3 is made, is the same as the speed that N2 and H2 are being made. Okay, and so once we're at equilibrium, again, that means you have those equal rates, the constant concentrations. That's always the case for equilibrium, but the environment that creates that allows for equilibrium to happen, isn't always there. So just like you, reactions can get stressed out. And so stress in terms of reactions just means change. So a change to the environment causing something to shift out of equilibrium. So we need to kind of fix it and relieve that stress. So just like you, if you get stressed out, you learn how to figure it out on your own and you move on and deal with it. Same thing with reactions. Though you guys get stressed with homework and tests and all this other stuff, reactions can get stressed with changes in concentration, changes in temperature, and changes in pressure. So in a reaction will have to figure out how to deal with these changes or this stress and counteract it by shifting the reaction, by either favoring the forward reaction or favoring the reverse reaction. Again, this is very conceptual, so you might be confused, but the more we practice with it, the more comfortable you will feel with it. And so the Chatelier's principle can be boiled down to this. It kind of looks like lyrics to like the cha-cha slide. Add to the left, shift to the right. But really what this means. And so let's say we have a reaction. Again, you're going to need these reversible reactions for equilibrium. So you can go forward and you can go backwards. And so when you're doing this, I like to think of the Waka Waka dance. And so if you look at her hands, if you're at equilibrium, the speed of the forward reaction is the same as the speed of the reverse reaction. So think about her hands kind of in the middle. But if one side becomes stronger, so let's say your right side becomes stronger, you end up pushing the reaction towards the left. And so this kind of dance is something that I like to use to think about it. And so if we kind of apply this, before we even do this, I like to add lefts and rights to my paper because it's a very common mistake and it would be a very silly mistake to make if you mess up your lefts and your rights. So we look at this first one. If we're adding to the left, we're going to shift to the right. And so here is the left. And so at equilibrium, again, the speed at which going forward and the speed of going backwards is the same. Okay, I'm going to stress out this reaction by adding more to this side. And so now the left side becomes stronger. If the left side is stronger, it's able to push the reaction that way. So essentially, it kind of gets rid of that other arrow, making it one way. So whatever side is stronger, just, hey, I'm the stronger side. I'm going to dominate and push my way that way. And so if we're pushing this way, we call that a shift to the right. That means we're favoring the forward reaction. If, for example, though, we do the opposite, so we add to the right, now the product side is stronger, and so it's able to push towards the left. And that's what we call a shift to the left. So if we're shifting towards the left, now we're favoring the reverse reaction, which means we're going to use up these, and so those concentrations are going to go down, and we're going to make that, which means we increase this. And so that is kind of the very basics of Le Chatelier's principle. If we were to, let's remove some of this. Again, left or right, and we remove from something. A plus B gives us C plus D. If we remove, let's say, from the left side, that makes the right side stronger, so we shift towards the left. It's all about finding out which side is stronger. Once you find the stronger side, then you know it pushes that way. Or it pushes from the stronger one to the weaker one. Things to think about. If you increase pressure, you're shifting to the side with the least amount of gas particles. If you see energy or heat, it's the same if you have heat or energy in your equation, which we'll work through examples like that. It's kind of wordy, but the side in which the reaction shifts is the side whose amount increases and the other side decreases. And so if we're looking at this example, again, we said we removed this, or we are removing some of that, so this side becomes stronger. And so if this side becomes stronger, we get that shift. And so if we're going this way, that means we're going to use up concentrations of C and D. So these brackets mean concentration. We're going to use up C and D, and we're going to make A and B. So again, we're going to practice this more, but it all kind of boils down to 4 letters. AATT, which stands for add, away, take, towards. And so whatever side you add to, you move away from. Whatever side you take from, you move towards it. And so that's kind of a way to remember it. And lastly, a catalyst does not cause stress. So you might see, oh, hey, does a catalyst cause stress? It does not. It just speeds up the reactions equally. So again, thinking of the Waka Waka dance, we'll talk more about this in class as to why this is actually applicable. But until then, this is the last video of Unit 9. Next time we talk, it will be about acids, bases, and salts. Until then, have a wonderful day.